Hi all, Mr. Yeager for chemistry. What I want to show you today is ice charts. So this is related to using the equilibrium constant, but this takes just a little bit more work, and this is something we have to write out in a particular way. Again, this is one of those things of, you might be like, well, I can just do it in my head and blah, blah, blah. You're going to be asked to write this out. Going to a college level, AP level, or college level chemistry class, you're going to have more complicated problems, and this is a nice organization way to see what is happening during an equilibrium problem, okay, from the beginning to the very, very end, okay? So ICE stands for initial change in equilibrium concentrations, basically charts, initial change in equilibrium. And it's supposed to show the concentrations of the reactants and products during the chemical reaction itself, okay? So that's basically, we basically write out what we have to start with. It might be giving you the equilibrium, it might be giving you the initial, but the idea is we have to see the change that occurs, and this has to be consistent across all of the different products and reactants themselves, okay? So the easiest way for me to do this is to just go straight to problems. It's not going to be worth trying to write it all out or show it, type it all out with anything. So I have this reaction here, okay? In the reaction, 2NO2 produces, or is at equilibrium with N2O4. The initial concentration of N2O4 was 0.1 molar, NO2 was 0.055 molar, and at equilibrium, the concentration of N2O4 is now 0.090, and it wants you to figure out what Kc is. We will almost always be calculating what Kc is. When you get to higher level chemistries, you might actually have to go in and solve for the chemical concentrations. That just involves, though, quadratics. So we are not going to do that on the test at all. I think I have a quick little lab activity for students to do where they look at that, but at this level in honors chemistry, I'm looking at you just to be able to understand and be able to set up an ice chart problem, okay? So the easiest way to kind of do this is to rewrite the reaction out. So 2NO2 is at equilibrium with N2O4. And again, this is already balanced. The coefficients were already there. What we then write is I, C, and E, okay? Again, I stands for initial. What is the initial concentrations if we know them? What's the change in concentration occurring? And then what's the equilibrium concentration, all right? So in this particular problem, well, let's write out what our K should be. Our K is going to equal, our Kc is going to equal the concentration of N2O4, no exponent, it's 1, over NO2 squared. All right. So what we have here is it does give us the initial amounts of both. It says the initial concentration of N2O4 is 0.100. All right. We do need to be in molarity. I'm going to do another one where we have to make sure we're in molarity again. Okay. The other side, we're starting with 0.055 molar NO2. Okay. It then tells us at the very end we have 0.090 N2O4. And again, this is why we make the chart, so I can see what's happening here. Okay. So I need to figure out the final equilibrium concentration of NO2 because I cannot plug 0.1 and 0.055 in. That'll give me the Q, but I'm not interested in that at all. That's not what we're looking for here. Okay? So I need to figure out the change. So, what I look at is obviously I can do this last column and figure out how much this changed by. It went from 0.1 to 0.09. So this went down by minus 0.010 molar. I'll put all the molars there. This changed by 0.01 molar, okay? Because that changed by 0.01 molar, we have to think what's happening here. And we're starting off with one already where it's like, I already threw a little thing in that we have to notice too. The other side will change by that same amount, but multiplied by any coefficients that it might have. Because again, the idea here is going back to when we talked about moles and chemical reactions and balancing. It takes 2 moles of NO2 to react, and basically this is a synthesis reaction. I need 2 NO2s to come together to form 1 N2O4. So this coefficient is what I'm going to have to multiply the change in concentration by when I need to, like for the ice chart. So I multiply the coefficient by how much the concentration is changing of anything that's only 1. All right, because there might be multiple things. So if this was 3, I mean, we'll go and write down. What's going to happen is, if this is going down by 0.01, this side must be increasing plus 2 times 0.010 molar. Again, that's because we're on opposite sides of the reaction. If one is going down, if I'm losing N2O4, that means the reaction is moving this way, creating N2O2. For every 0.01 molar decomposing, I'm getting 2 0.01 molars of NO2. All right? And again, you might not see it. You might be like, I have no idea what he just did. Again, I'm looking at the fact that the problem, I'll kind of erase this part. I'll go back and show this one more time with it. These are all the numbers we were initially given. We know the initial concentrations of the reactants and products. We know the final concentration of the product. Based on the initial and final concentrations, I know the N2O4 decreased by minus 0.01 molar. So the other side has to change by 0.010 molar plus times any coefficients it might have. If there was only 1 right here, it would just be plus 0.01, but this is times 2. So I'm going to have 0.075 molar NO2 at the end of this chemical equation. All right? And again, I will tell you when you need ice charts. It'll say in the problem and say, use an ice chart. Use an ice chart. Unfortunately, if you're watching this and you have a different teacher, maybe not. There is a rule basically where if it changes by less than 5%, you don't need an ice chart. Again, that's like a general rule of thumb. Technically, we should still use an ice chart, but it's going to be so minor, the change in the difference between the products and reactants occurring, that you will really not see any difference whether you show that change or you didn't. But if there is a greater than 5% change, then we should use an ice chart. In this case, I'm changing by 10%, so we should be using an ice chart. So finishing up, Kc equals, my final concentration of N2O4 is 0.09 divided by 0.075 squared. And, sorry, get my calculator here. 0.09 divided by 0.075 squared is 16. And there's my equilibrium constant, 16. Okay? So let's try to find one more. I want to do one where you actually have to calculate out. We're going to find one with a 2-liter container again. All right, maybe I think I have one down here that's 0.5. Yeah, it's like this one. There you go. All right, so here's a good one. Let's see here. 0.5 moles of X is placed into a 0.750 liter vessel. At equilibrium, there are 0.350 moles of X left. Calculate Kc. And this one jumping right to a really difficult one with 2, 3, 4 being the different coefficients. I'll tell you, a lot of the ones that I usually practice in class, they're pretty straightforward. A lot of 111s and stuff like that. So if we're doing these more difficult ones, you should then hopefully be able to do the easier ones. So Kc in the end is going to equal y cubed times z to the 4th. Oh, I don't know why I put it in there. Z to the 4th divided by x squared. All right, let's write my ice chart out. So I got 2x at equilibrium with 3y plus 4z. Now this is, I guess, a little bit nice because it's only giving you the one number, and so we're starting off. Oh, I do need to find molarity. See, I almost made my own mistake. 0.500 moles divided by 0.75 moles. The nice thing you do this, you don't have to do it at the end. You're not sitting there going, oh, I need to divide by 0.75 again. Sorry, liters. So once you do this, everything will be a molarity from here on out. So this should be 0.67 molarity. Okay, 0.67. That's not a very nice number to give us, especially with the amount they're giving us here. Yep. All right. But the other side, 0, 0. Okay, we're not starting with any of those. It says at the end we're going to have 0.350 left. All right, so this one's a little bit more difficult. We got to think here, okay? Because we can subtract these two. We can find that the change is 0.67 minus 0.35, which comes out to what? 0.32? Okay, that's actually not a bad number then. I thought it was going to make it more difficult. It's going to change by 0.32. But this is, the change here is after I multiply the 2 moles of it. So basically what I'm saying is 2 times the change equals 0.32. So I need to actually divide that and say this is 2 times 0.16. That's how much this is changing by. Okay? 2 times 0.16. I need that number because it's the 0.16 that's going in on the other side and going to get multiplied. So this is going to be 3 times 0.16, and this is going to be 4 times 0.16. This is going to be added. Whichever side is subtracted, the other side is added. So this would come out to 0.48 molar, and this would be 0.64 molar. All right? I hope you see that okay. All right? And again, these are the final concentrations, are these 3 down here. That's your equilibrium concentrations. So again, what did I do? I found that the change was 0.32, but that is 2 times whatever it's actually changing by. It's 0.32, so 0.16. Okay? Then I can plug it on in over here. Kc equals 0.48 cubed times 0.64 to the 4th over 0.35 squared. So 0.48 cubed times 0.64 to the 4th divided by 0.35 squared. And the Kc here is 0.151. I don't know why I did point. Oh yeah, it's 366. Yep. So 0.151 in the end. All right. So that is your ice charts. Okay. You have to just do ICE, ice, initial change and equilibrium. Take your time to see what the change is occurring. Make sure you pay attention to the coefficients. If there's coefficients, that you actually have to multiply the change that's occurring by that number. Or in this case, we actually had to divide it to figure out what the change was. All right. And again, it's because we have to pay attention to the mole values that are basically occurring here too. Okay? So that's essentially it for ice charts, and that's it for equilibrium. Thanks.